Hello and welcome back to the MCAT grind. We have Chapter 5 of General Chem about chemical kinetics. Kinetics, you will see definitely one question showing a graph showing the compounds A and B or perhaps C and the rate. And you will be asked to determine the rate and the rate law for this following reaction that's determined experimentally. Now to start us off, we have the Arrhenius equation, which tells you that the rate is determined by A, which is the the reaction constant, times the collision constant, times E to the power of epsilon to the power of activation energy, right? Activation energy, that's energy required to overcome that first for the reaction to proceed. That's the limitation, as well as divided by R, the gas constant, 8.315 joules per mole K, and times the temperature in Kelvin. So you can see that works out because 8.315 joules per mole K, joules over the temperature, so that cancels out, joules and joules per joules cancels out, and the overall reaction should be K per mole. Alright, then we have the rate. The rate is determined in moles per second, like molar per second or mole per liter per second. And the rate law is in the generic form of K, the constant, times A, and B to a certain constant. Now, if it's a zero order, where the adding different reactants doesn't really matter and it's just always constant, such as, let's say you have this mysterious substance that you put in a solution, and then whatever you add to it, it's just going to always melt at the same rate, right? This mysterious cube is only going to melt at a certain rate. It doesn't matter if you add more of this in, doesn't matter if you add more solution in, it's just always going to dissolve at the same rate. So that would be in zero rate law order. A first rate law order is if you add more, perhaps the solution to it, it starts dissolving faster. But if you add more of this compound, it doesn't dissolve faster. A second rate law, to second order, will be every time you double the amount it has, it's going to increase the rate by a factor of 4. So 2 to the power 2 squared. So 2 to the power of 4, or to the power of 2. So it's going to square it, and every time you double, it basically quadruples the rate. So look at this. If we have reactant 1 and reactant 2, and it gives a rate of 2 molar per second, and if I double B, that increases the rate by 4. So we know B is to the power of 2. If we double A, that doubles the rate of A, the overall rate, by 2. So we know it's in the first order because it follows it, right? You double it, it doubles. So we know the overall rate is K, A times B squared. Now there are some parts to memorize here. We have half-life, which determines that at which time, half-life is the time at which the thing is divided by exactly half. The original compounds, the amount of it is halved exactly. You might have heard of half-life of a radioactive decay. What's the half-life time? How long it actually takes for the original compound to divide by 2. For this one is, for 0th order, is divided by 2k. K is like the constant. And for the first order, it will be ln 2 over k. And for second order is 1 over k, A initial. The integrated rate law, and these rate laws can be plotted on a graph for you to better visualize. If you think about it, initial A will be up here, and this is really just glorified y equals mx plus b, right? Y, that's like how it is at any point in time. Mx, the rate is basically in m. X is time, right? It's versus time, obviously, and B is just what it started off with. So it's going to decrease in concentration over time, right? And it's going to decrease in concentration over time. And at exactly this point of the triangle, right? That's why it's half of K here. That's where you can extrapolate the time where there's exactly half of it. Okay, and that depends on the slope of K, the time at which it happens. And first order, because it's relative to what the concentration is at any given time. It's in a long graph. And you can see ln A, where it starts off, it's also going to plot a straight line if you long the original product to where the ln product currently is, and in a mx plus b format. Now in the original, if you don't long it and you E everything, exponentialify everything, you get a radioactive decay equation here. The current amount of compound is equal to A initial times E to a negative K times the time in a first order radioactive decay reaction. This might be familiar to you. Second order, you will have to work backwards because it's a 1 over, so it's a reciprocal. So the K is positive this time because you're reciprocaling, and as you get higher and higher, the reciprocal gets bigger and bigger, right? Because the less compound you have, the reciprocal of that is going to get bigger and bigger. Great, and this is just for better familiarity as to where the slope is, right? And the initial amount, where it starts off as. And they plots as straight lines for better calculation. Alright, and that's all for chemical kinetics.